Okay.
Let's do it. So we're into at the end of this week now. We kind of wrapped up 7 point or chapter 7 really fast. Worked our way through chapter 8. Sort of learned a little bit along the way, but we'll get there. And now we can start moving on to chapter 9. We're going to learn these first 2 sections, and we're going to test on some of the other things on Monday. So, so here, right, we've written modeling with differential equations. Okay, so we saw a bit earlier, right, that what a differential equation was, or kind of got into the notion of it when we were talking about this differential equation for population, which I don't know why. There should be y, but we worked with this dy over dt equals ky equation, right? And at the time, right, we could look at this equation and think through it, and we could say, oh, well, this does have a solution, right? That which was CE, or sorry, AT in that case, right? So we had this differential equation, right? And we had a solution to it, and we kind of worked with it at the time, but now we're wanting to get a little bit deeper into the subject, talk a little bit more about what differential equations are exactly and what we can do with them, right? Because this only barely scratches the surface of what we can do with these things, right? When we were working with differential equations, they were all essentially of this form in some way, and so we just kind of played around with it to make it work. But as the section says, we can model a lot more things than just growth with these differential equations. Okay, so again, we've already kind of covered this in depth, so I don't need to go through this, right? But the first example that we'll give, and maybe I can't remember if I gave a definition of the differential equation there, but maybe I'll write one here. An equation contains the derivative of a particular function which function needs to be found. Okay, so I think it's kind of stated. Okay, so a differential equation, right? We're talking about differential, right? We're talking about when we talk about differentiating, right? We're talking about derivatives, right? A differential equation contains the derivative of some function, right? Usually it's just dy over dt, but the derivative is within the equation, and my goal typically is to be able to find this function, right? This function which we're looking to find. We're not wanting to just have the derivative, but we want to find the function is, right? And in typical cases, right? We would have seen these before, right? Again, obviously here, or we've worked with things before where we said, okay, well, I know the derivative of some function is going to be t cubed minus t squared or something, right? And this is still a differential equation. Now, it's not a very hard one, right? Because I'm just saying the derivative of a function is t cubed minus t squared, right? So if I want to figure out what the original function is in this case, what do you think I should do to find it? If this is its derivative, we just take the integral straight, right? So maybe first we think about maybe bringing this dt up here, right? Just integrals make more sense. But yeah, we would just essentially just be taking the integral of this thing, right? So our function is just the integral of this. What's the integral of t cubed minus t squared? Absolutely. So this would be my function, right? Which would solve that, right? And those are pretty easy to solve, right? If I just have dy over dt equals t cubed minus t squared, I just take the integral and that's going to be it, right? But as we see in this example, we're going to see in further ones, I don't just have, dy over dx is something, or dy over dt equals something of t. I might have the function itself there as well, right? So I need to do the work to be able to solve for it, right? And so in this case, we kind of talked through it. It makes sense and it worked, how we could get to our conclusion. But maybe it's worth noting here that this situation, right, this population situation assumes ideal, this is like the ideal growth pattern, right? Where it can there's always an unlimited amount of resources. There's always everything they need, so they can just continue to grow without any sort of issues, right? But that's not the case oftentimes, right? Sometimes you have it where a population is going to grow to a certain size, grow big enough to where there's no more resources for them, right? So they can't continue to produce to sustain everyone, right? And that's when in this equation we need to bring in this thing called the carrying capacity. We'll call M. Okay, typically M is the way we denote that. Okay. Now this still kind of gives us the general idea, right? That when a population is growing, it should grow in this form, right? But also I need to recognize that once we hit this sort of carrying capacity for the people, that things should start decreasing, right? And so the way that they put this together is actually the way we model this, right? Is we start off with y, but then we're going to add on an extra term. It's going to be 1 minus y over m, or you might have p in this case. But this is probably a better representation of population growth, right? In the sense that whenever the y amount is small, when we have a small number, this m should be pretty big, ideally, right? It still would hopefully be a large number, right? When y is small, it's still basically this, right? Because if y is a small number, you're subtracting barely anything from 1. So we're still behaving like that system would, right? But as it gets bigger, this is going to become a bigger deal. And as soon as we pass that carrying capacity, right, what's going to happen is my population is going to start decreasing a little bit because it's kind of overshot the capacity. So things are going to start getting a little more interesting, right? But this is the system, right? Now, if you tried to say, okay, well, maybe that same solution still works, the unfortunate problem is it doesn't, right? And I can just look at this thing and be like, okay, well, that's great, but ideally I'd still like to be able to know what the population is going to be like at each time. And this equation really can't do that for me anymore. Or that solution can't work for me, right? So the question is there a way I can solve this? Is there a way I can find that, right? And we will actually be able to solve this sort of system next week. But for today, we're just kind of talking about these different situations and these different models and how we can work with them, right? But we can still take what we have and kind of get some interesting information out of it. In this case, right, I have this equation, and it would be interesting to know, on a regular graph, right? What do we call these points on my graph? What do we call them? Not inflection points necessarily. The inflection point would be here, right? The inflection point is where it goes from being concave up to concave down, right? Right, it's kind of our max and mins, and we call those critical points, right? So we have critical points of a function that tell us where the biggest behaviors kind of happen, like where the biggest changes occur, where the most points of interest are, right? And to find what these are, let's remember, so let's say this is f, right? This is y equals f of x. If I wanted to find where the critical points were, what did I have to do? Yeah, exactly, right? And that would be where my slope is 0. So I'm going to take the derivative of that, set it equal to 0, right? And that would give me my, again, I'm going to go right here, critical. Good. So with this same, we can take this same idea and apply it here to still understand what these sort of critical function values are going to happen at, right? And using that here, I'm going to get what's called equilibrium solutions. And equilibrium solutions are solutions that make dy over dt, or whatever the derivative is at the time equal to 0. Okay? So these equilibrium solutions can tell me a lot about a system and still, in terms of what's the point I need to focus on, what's gonna, where is the biggest change gonna occur, right? So let's just take our system here as an example, right? So I have dy over dt equals ky times 1 minus ya. So if I want to take this thing, I want to find its equilibrium solutions. I just take it and I set it equal to 0. Okay. So if I set it equal to 0, what can I do at this point, right? Can I figure out what the y's are going to be from here? What needs to happen? Right? I'm solving this equation here, right? So you could divide by ky only if y is not 0, right? But y could be 0 in this case, right? So we need to be careful. But it's still, right? We have two factors, right? So what do we know about what happens if I have different factors multiply and they're equal to 0? Yeah, I'll just set both parts individually equal to 0. So I'm going to have ky equal to 0, and I'm going to have 1 minus y over m equal to 0. Right? This is just how we solve quadratics, right? You factor it, and you can get the solutions when you set it equal to 0, and that gives us 2 parts, right? So what's y going to be in this case? Y is 0. So that one, I mean, yeah, I still wanted to acknowledge this one here. It's not really too interesting. I mean, it's just a starting 0 population, but still is an equilibrium solution for the system. How about this one? What is the solution going to be in this case? Yeah, it's going to be big M, right? And you can work that out if you want. I can add the y over m to both sides and then multiply, but I'm just going to be left with that big M, right? So, which makes sense, right? The carrying capacity should be when everything starts going downwards, right? And so that's going to be my one of my equilibrium solutions, right? I take both of these in. So these are both solutions to the equation, but they make the derivative 0. Okay, there's going to be other ones that don't do that, but these do. Any questions on this at the moment? Is that good? Okay. Fantastic. Let me give you another example of an interesting sort of differential equation. Which is involved in modeling springs. Okay, so you may have taken a physics class at some point where you would have seen this equation pop up, but springs have what's called a restoring force. Is equal to negative k times x. Okay. Now, what this means is, so k is like the spring constant, or like the stiffness of the spring, right? And x is the distance that if you take that string and that spring and you stretch it, right? That's the distance from its kind of equilibrium state, maybe in a way, right? Where it's just you have it sitting there, you're not touching it, right? X is how far you stretch it from that point. point, or maybe squish it from that point. So in that case, we'll just make the slight adjustment to say, okay, the spring is this stiff, so it might take this long to, for it to come back to its equilibrium spot. Okay, but this is the restoring force for a spring. This is the equation we use. The negative is just because if I stretch it out, for example, you should expect the force is going to act in the opposite way, right? It's going to pull the opposite way. Okay, now, how does this turn into a differential equation for us? Well, we also know that force in general of an object, according to, I think it's second law. I couldn't remember which is which. But force is the same thing as if I take the mass of an object and I multiply it by its acceleration. Okay, so again, if you've taken a physics class or going to, you're going to see this equation pop up: mass times acceleration, that is force. Okay, if an object weighs a certain amount or has a certain mass, the gravity on it doesn't matter too much here, and then it's moving at a specific speed, then the force applied to it is m times a. Now, the acceleration, right? So I think this is section, I think this is maybe 2.7 in this book. But we talked about position, velocity, and acceleration, right? And how they're related to each other. I think there was a section in chapter 4 about it as well, right? If my position, right, we represent as S of t, right? So that's my position. How does that relate to my velocity? What is the velocity in relation to the position? It's the derivative of it. So the derivative of S of t equals v of t. Okay. Now, how does the acceleration relate to the velocity? It's the derivative of the velocity. Good. Be a of t, which this is also the same thing as the second derivative of the position. Right? But that's the key thing here, right? The second derivative of my position is my acceleration, right? Now my position, when I'm talking about springs, is how much I stretch it out, right? So the acceleration of that spring is related to this x as it is its second derivative. Okay, so that just comes from what we learned before. We know acceleration is the second derivative of the position, right? So here's x, and then this is the d squared x over dt squared. Okay, so I need these two things to be equal, right? Because they're two different representations. So what ends up happening is I'm going to get m times d squared x over dt squared equals negative kx, or maybe I can write this as d squared x over dt squared equals negative k over m times x. So this is an equation to model the movement of a spring, right? To model, okay, I pull it out this much, and this is how much it's going to fluctuate, right? Of course, including the k and the m to help us just adjust for the different path, right? Now, this is what we call, so this type of equation is what we call, this was a, maybe I'll write this right here so we can know it. First order differential equation, which is going to be the ones we're working with in this chapter for the most part. Okay, and this one is called a second order differential. Okay. So the reason why this one's first order is because you only have the first derivative, right? But this one's called second order because it has the second derivative, right? You can have as many derivatives technically in your differential equation as you want to the second, third, fourth, fifth, however far you want to go. But we usually like to study the first and the second because those ones are a lot easier and a lot more common. Having a differential equation with a third derivative doesn't happen very often. Yes. What is a partial differential equation? Nothing you need to worry about for a long time, but it'll make more sense once you get into Calc 3. But right now we're working with two-dimensional systems, right? Where you have a function of x, y equals a function of x, right? But whenever you get farther on, you get z equals a function of x and y, right? And so in that case, you have two different variables. So you want to study the derivative in one direction and study the derivative in another direction, like study two different directions, essentially, two variables. Again, we don't have to do that here. You don't have to worry about that. So, but that's since you have more variables, you have more things to worry about. Okay. Any questions on this front? Right now? Yes.
That equation is equivalent to differential equation.
This one?
Yeah.
This is not equivalent to the first. This one, yeah, this is a first order, that's a second order. They're not related in any way. Now there are some cases like maybe if I just have a second order and a second derivative and the first derivative in my equation, that I can model it in that way and then work from there. But in that I can't do that here. Okay, so I have to treat them differently. Which again, we don't cover this time here, but it's interesting to see it at least laid out. We're going to cover these types because these are the ones we can solve. Any other questions? Okay, cool. I'll mention while I'm kind of erasing some stuff here. The solution to that, even though we can't technically solve it, isn't actually too hard to guess. If you think through it, right? Let's remember what a spring does, right? If I stretch it out, it's gonna go down, but it doesn't just go down and then stop, right? It usually kind of fluctuates, right? So we want some sort of function that's going to be periodic in some way, that's going to have like a wavy motion, right? So the idea is, oh, well, the functions we know like that are sine and cosine. And actually, that would precisely work in this case if you pick the right variable, right? Because what if I think it would be this, right? Because what's going to happen when I take the derivative twice, I get sine as cosine, and cosine is going to be negative sine. So that gives me that negative sign here, right? That's where the negative sign comes from. And then each time I take the derivative, I have to multiply out as square root of k over n. And so that's actually the solution to that. So not actually too hard to kind of guess and think through, but in general, right, we're going to have a lot harder ones that you can't just kind of think through. And I wouldn't say most people could even just be like, oh, of course, but just if you're curious. Okay. Now, moving on. In general, right? We model a couple cases, but obviously there's a lot of things that we'd like to try to model, right? But I'm going to be getting some pretty crazy, sort of equations and stuff that it's not going to be very easy to look at them and be like, oh, of course, that's what my solution is going to be, right? And we still want to be able to find the solution. We're going to find ways to do this, but it's important to just know how helpful these are going to be to us, right? This section just kind of goes through and just be like, here we have these differential equations. We need to be able to solve them. So all we're gonna start on doing now, just as we're introducing the subject, so I just gave you this harder looking one, right? We don't know how to solve it. But the book is just gonna have some examples, which I'll go ahead and just do some example, an example for you here. I'll do number 6. Book, okay? Where we're gonna just study an example of a differential equation, they're gonna give us solutions to it, right? And they're gonna say, show that this is a solution. So number 6, and then this has several parts. I'm gonna skip over part B for now. But we're going to show that every member of normal functions and we're going to have y equals the natural log of x plus c over x is a solution of differential, and I'll just write diff q, differential equation just for short. And we have x squared y prime plus y equals, okay, so it is our goal to show that this function, this family of functions, right, because we have a plus c, so c could really be anything, some constant. We want to show that this is going to be a solution to this function, right? So in order to do that, we just need to plug things in and to show that it works, right? For right now, that's really all we're going to do. So let's take our function, right? And again, we're going to put it in. We notice there's a y here, so I can just immediately put that in, but I need to get y prime, right? If I want to find y prime of this function, how do I take the derivative of this thing? What rule do I need to use? Quotient rule. Good. Now, what does quotient rule tell me to do? So we're going to take x times the derivative of the top. What's the derivative of the top? Good. X times 1 over x minus times ln x plus c. So I mean, make sure ln x plus c so there. And then we're going to divide this by what? X squared. So we're going to get x times 1 over x, 1 minus the natural log of x minus c, which is going to be important to distribute that here. And that's all over x squared. So that is our derivative. Okay, so funny enough, it just makes that for subtracting and puts a 1 there. Now, I'm going to take that, I'm going to plug it in here, right, along with my function. So I'm going to get x squared times 1 minus ln x minus c over x squared plus x times ln x plus c over x, and we want this to be equal to 1. Okay, so what's going to happen to my x squareds? And what's going to happen to my x? Cancel. Good. So I have 1 minus the natural log of x minus c plus the natural log of x plus c. So is this a true statement? Absolutely. This natural log and this natural log cancel, and this minus c, this plus c cancel. So this truly was a solution, right? And that's it for that problem, right? You just have to do the derivative and plug it in, right? We just want to confirm you can do that. You understand kind of what we're looking for here. So somehow someone was able to take this thing that looked seemingly hard and find a solution for it, which in this case was the natural log of x plus c over x. And we just confirmed their finding. Okay. And this is going to be very useful to have, right? I mean, for the system, right? so that I don't just have to look at this, I can say, okay, this is what my y is doing, right? This may be how it and its derivative are related, which is nice to see, but also just knowing the path itself is going to be helpful. Good. Okay, again, I'm gonna skip part B, which just says you could like illustrate like by graphing several members of the function. So you could just plug in different c's. You could do 0 for c, 1 for c, whatever you want. Just to kind of see what happens. Just kind of see what this curve looks like and just really think about, oh, like all those different things solve this. It's pretty interesting. But we're going to go ahead and we'll do part C. Okay. So part C says find a solution that satisfies the what's called the initial value condition, which given to us here is y of 1 equals 2. Okay. So whenever we're talking about initial value conditions, or I'm going to write this here as an initial right? Notice we're working with derivatives, right? Eventually, when I integrate a derivative, you know what? When I get rid of that derivative, I should be able to have my function. Most of the time, when I take an integral, there's going to be a plus c or some sort of plus c term involved, right? And so there's a lot of different options, right? And so in some specific case, right? So for example, in the spring problem, I could have been given, well, x of 0 is 0, right? Whenever I'm at time 0, I should be at position 0, right? That would have helped me to get a more solid solution that's going to more represent my system rather than if it started more stretched out in some way, right? So an initial value problem is equation with 1 point of the solution given. Typically, the initial point, like y is 0. Sometimes we're not given that. Sometimes you're given y of 1, or in this case, it's y of 1, y of 2, or sometimes you're given y of 37. I don't know. Depends on the problem, I guess. But in general, right, it's a differential equation, and then we're going to be given. We're wanting to say, okay, I want to find the solution to this equation that passes through this particular point. So I don't want to just use any plus c. I want to find the one that's going to give me exactly what I want. Because I know that this thing models my system, but I need to make sure I know, do I have like a starting point that I can attach it to, right? Because I don't want it to model my system, but really be way off my starting point, right? I need to have it based in reality, based in starting point, and from we can go from there, right? So for part C, I want to find a solution that satisfies this condition for the initial value problem to solve this, right? Now, we were given this family of solutions, right? It's this family of solutions that solves this differential equation, right? Which is great. But I want to find one of those in that family that's going to work for my y of 1 equals 2 case, right? So what I'm going to do is I'm going to take this and I'm going to plug it in to my equation, right? To this solution, right? That I would have found, right? So we have y of 1, 2, which is going to be equal to, right? Because that's y. We're going to get natural log of 1 plus c over 1. Just like that. Okay. What is the natural log of 1? 0. Good. And then you divide by 1, it's just 1. So we get 0 plus c So what is C going to be in this case? So C is going to be 2. Good. So the solution that satisfies the initial value conditions here is going to be y equals the natural log of x plus 2 over x. So that would be my answer. Okay, that's the initial condition I wanted. So I just plugged in the values. I found the C that made it work, and we get it. Okay, does that make sense? Right. Oftentimes you'll actually have to solve the problem and then plug in the value later. But for now, they just give you the solution. So it should be pretty straightforward. Okay. For now, let's just do another one real fast. Right, and I'll make. Let's see. I'll just. Because we'll just go ahead and do part D as well. So part D in this case says that we want to find a solution that satisfies y of 2. Okay, so we're just going to do the same thing again, except now we're given a different condition, right? So, and putting 1 in made my problem a little easier because I had the natural log there, but now we might have to do a little bit more work. Okay, so I'm going to write down the family of solutions, right? Okay, where's the 1 going to go? Go in place of x or y? What is it? Y. Yeah, it goes in place of y. So we get 1 equals, and then where's the 2 go? In place of x. So I get the natural log of 2 plus c over 2. Okay. So I want to solve this for c, right? How do I do that? Good. So we get 2 equals the natural log of 2 plus c. What's left? Log 2. C equals 2 minus natural log of 2. And so thus our final answer, which is put over here, is going to be y equals the natural log of x plus 2 minus the natural log of 2 over x. And that's it. Okay, so that is the specific solution in that family that's going to solve it. Okay, any questions? Absolutely, yeah. We could do natural log of x minus natural log of 2. So I could do like that. And that's also sorted out. Anything else? I guess not. Okay. Well, that's the end of the first section. So there you go. If you have any other questions, you could ask me in the meantime, but I'll give you like a 10-minute break here. Next bit. See, today's a lot easier. We'll move on to the next section. Yeah. Okay. Oh yeah, I'll stop real fast. Okay.